Okay, great. Well, that's a beautiful looking slide. So thanks, Carlo. We'll hear more about loop integrals in the soft region and gravity eikonal. That's great.
Thanks a lot. And let me start by thanking the organizers for the opportunity to present this talk. Most material that I'll be covering is in these papers together with Paolo Di Vecchia, Rodolfo Russo, and Gabriele Veneziano. And the idea is to present some techniques that have been useful in the evaluation of certain loop integrals that emerge in particular in the connection between scattering amplitudes and classical gravitational wave observables. And of course, I will be touching upon many aspects that Mao also brought up in his very nice talk. But particularly the angle to this problem that I'll be approaching the problem from is the one motivated by the eikonal. So I would like therefore to start by a quick reminder of this eikonal approach that allows us to start from the scattering amplitude and retrieve its classical asymptotics in impact parameter space, and eventually leads us to the calculation of some observables. In particular, we're focusing on the deflection angle chi for the classical two-body problem. And hopefully this will further motivate, although probably at some point this is not so much needed, our necessity to have a firm grasp on the expansion of loop integrals in the limit in which the momentum transfer goes to zero. In particular, on the interest will motivate for us the interest in the soft region. And before moving on to some more technical aspects, I would also like to flash some recent results, in particular tracing some path in the recent literature, in particular the one related to this eikonal approach. And finally, I will present some more technical aspects that have to do with this business of equations, differential equations that Mao was also mentioning. So one very successful strategy to evaluate these integrals has been to set up ordinary differential equations essentially in the velocity variable, or in this relativistic gamma factor sigma that I will be using. And then essentially one is left with the task of evaluating these boundary conditions as sigma tends to 1, as we have seen. And I will try to illustrate basically some tricks that we have been using to do this in the toy example of the box at one loop once again, and also in this slightly more real life two-loop example of the sometimes called the double triangle prime. So let me start by briefly recalling the problem that we are interested in once again, just to get everybody on the same page and essentially fix notations. So we are interested in the collision of two bodies with masses n1 and 2 that fly past each other with some initial momentum p, and eventually asymptote to some new direction, slightly deflecting from the initial one, p prime. And the observables we are going to be interested in this setup is in particular this momentum transfer, classical momentum transfer bq, and or this deflection angle here. And also to this level of approximation, of course, this q perpendicular is related to chi by this relation with the sign of chi half. And also the momentum, the impact parameter b comes in two slightly different flavors. One is this bj, which is directly orthogonal to the incoming momenta, and therefore directly gives you the angular momentum of the problem, or this so-called also eikonal impact parameter b, which is related to bj by the cosine. In the drawing, the two green lines should be parallel, so bq should be parallel to b. Now, the way we are going to approach the problem is slightly roundabout, in the sense that we want to start from an object which is to some extent very far away in our space of physics knowledge, which is a scattering amplitude. So in particular, this elastic scattering amplitude, of which I've drawn a cartoon on the right, and this amplitude is usually regarded as a function of two models, time invariance, S and T. So again, let me just quickly fix notations. S is just the square of the center of mass energy, so P1 plus P2 squared, and sigma, this variable I was mentioning earlier, is given by P1 dot P2 I'm using mostly plus, sorry, conventions. And again, in terms of the relative velocity, this is given by this expression. So v is the velocity of either particle in the reference frame of the other particle. And then the momentum transfer in the amplitude is simply given by P1 plus P4. I'm using these slightly weird conventions whereby P1 and P2 are taken to be path directed, but bear with me. And T is equal to minus Q squared. So to describe the scales of the problem, let me fix some reference energy scale M star, which characterizes this scattering. And we can take it essentially anywhere between this center of mass energy and the masses, M1 and M2. And now we expect the system to behave classically in the regime of large quantum numbers, or in the range of angular momenta, which we can take given by this expression, much larger than h bar. So this is the regime in which we expect classical physics to be valid. And now if we compare this condition with the usual way in which we calculate the amplitude, namely in a loop expansion in powers of g Newton. So this is a 3-level, 1-loop level, 2-loop level. We see that these two are very different, of course, because this g times reference scale squared, much larger than h bar, is actually clashing with this small g expansion, that small g quote unquote, of course, expansion that we usually do for the amplitude. So this seems like a very hard problem, a very hard thing to do. Now, a way to simplify the problem and retrieve a classical flavor to these kind of calculations is to consider also impact parameters much larger than the typical size of the two bodies, in analogy with the Schwarzschild radius GM star. And this will be for us just the post-Minkowskian, expansion, which G is small in this particular sense. So to reiterate, the large classical scale is given by this expression. The small post-Minkowskian expansion parameter is given by this expression. And let me also rephrase this as a hierarchy of length scales, which sometimes is more easy to visualize. GM star much less than B. And to be precise here, I should also put some scale to the 2 epsilon, since we are usually working in dimensional regularization. Let me put the impact parameter itself. Now, to solve this apparent tension between the small g expansion and the classical limit comes the eikonal to our rescue, essentially. So the eikonal instructs us to look at the amplitude in impact parameter space, defining a Fourier transform of the amplitude with respect to Q. Particularly this Q perpendicular in this 2 minus 2 epsilon transform, because this Q perpendicular is supposed to be perpendicular to P1 and P2. And the idea is that the right asymptotics of the amplitude are captured by the following formula, which we can think of as an ansatz, in particular 1 plus I A tilde, this impact parameter space amplitude, should be equal to e to the 2I delta, 1 plus 2I delta being lowercase and uppercase delta. And the meaning of this formula is the following. So small delta is the eikonal proper, or also eikonal phase sometimes, and its expansion in powers of g is given by this form. And the leading eikonal scales precisely as this classical scale, as we defined before, this gm star squared over h bar. Then the subleading eikonals are simply suppressed by post-Minkowskian small factors. So gm star over b, gm star over b squared, and so on. So this is a purely classical object plus small post-Minkowskian corrections. On the other hand, this big delta is supposed to be a quantum object. So in its h bar scaling will be something like h bar to the 0, h bar to the 1, with appropriate powers of gm star to get the right post-Minkowskian and or dimensions, post-Minkowskian order or dimensions. Now, how do we retrieve this information from this apparently completely different loop expansion of the amplitude? Well, we simply expand back this formula formally in powers of G, treating it as formally small once again. And in this way, we find a number of relations between the usual perturbative expressions and the eikonals. So, for instance, 2I delta 0 is related to the 3 amplitude in momentum in impact parameter space. The one loop amplitude is given by this expression. The 2 loop amplitude is given by this expression. Then there is these are terms that arise from higher powers, of course, of the higher order expansions of the exponential. Then there is a classical piece that contains both a delta 2 and then an interference between the small delta and the large delta. And then again, some 2 loop remainder. And in principle, this goes on. Now, so this is the 1 p.m. level of the analysis, this is the 2 p.m. level, and this is the 3 p.m. level, which we'll be mostly interested in. And so what is the status of this? This has been already mentioned, I think, in Rodolfo Russo's talk, but the exponentiation of delta 0 has been actually proven, so that I think -1, its very leading classical piece should scale in this form. So this is a fact. So if you calculate an amplitude that does not have this property in impact parameter space, it means that you have done some mistake. Delta 1 should also be under control in the literature, whereas the exponentiation of delta 2 is a little bit more uncharted territory. So in fact, delta 2 has already some slightly less satisfactory property, namely it's not really a phase, as I was calling it, but it's really a complex number. So it has a real part and an imaginary part. And in fact, this imaginary part is infrared divergent. So this imaginary part has to do with the fact that, to be more precise, we should also include emissions, of course, of some real massless objects in the final states, and we cannot really live with the elastic amplitude only. But nevertheless, this quantity encodes already a number of interesting informations. For instance, it determines for you the zero frequency limit of the gravitational wave emission spectrum, and it's also related to radiation reaction effects that one can basically read it from there. Also, we can basically get away using the following trick. So now, since eventually we are interested in the transfer momentum big Q, we can go back to impact parameter space. From impact parameter space to momentum space, and determine the preferred classical Q from a stationary phase approximation. And in this stationary phase approximation, Q becomes determined by the derivative with respect to this impact parameter of 2 delta, or more precisely of the real part of 2 delta. So this is basically because only the real part contributes to the oscillations in this phase, indeed. And this seems to be the right recipe to get the right Q perpendicular from the eikonal, and then eventually the scattering angle. So this was just, again, to rephrase the problem and motivate the calculations we are going to do. And in particular, the 2 key points that I want to emphasize once again is that we want to evaluate these quantities for large impact parameters, and therefore for small Q. In fact, here Q small means Q essentially small with respect to this reference scale that I was mentioning. And then again, as was also already explained very well by Mao, we can basically throw away anything that is of the form Q squared to the 0, to the 1, to the 2, and so on, because this will only be localized with something that is localized at b equal to 0, anything with some support at b equal to 0 in impact parameter space. So let me illustrate this point. Again, I will be inevitably covering something that Mao already presented, but again, bear with me for a few minutes. So let me start from the simplest non-trivial example where some of these things emerge, which is once again the box. Let me go through this a little bit. So we can take the routing in this form, and this using the mass shell conditions translates into an integral of this type, L squared minus 2p1L, L squared plus 2p2L, L squared, L minus Q squared, where the I epsilon prescription should be minus I0. Although I leave it implicit for simplicity. So here, what we want to do is that we want to take Q much smaller than M star, and let me assume that although there are subtleties associated to Minkowski signature that in principle are non-trivial, let me assume for simplicity that P1 and P2 can be formally regarded as order M squared themselves, M star themselves. We want to perform this limit, and we can invoke the method of regions. So in particular, there will be a hard region, which means that we are instructed to expand the integrand of this Feynman integral in the formal scaling limit L scaling as M star itself. So basically scaling in a trivial manner with respect to Q. And this will just reduce our integral to this form, where we can neglect, in the very last denominator, we can neglect, sorry, I shouldn't have copied that. We can neglect Q. Now, again, by construction, this is, of course, Q independent, and in general, hard region contributions will be precisely of this type that we were mentioning earlier, and which we can simply throw away. More interesting for us is going to be the soft region, where L instead scales precisely like Q, and which, of course, by construction is going to give us non-analytic pieces in Q squared. And here it's particularly convenient to introduce some rescaled variables. Here, since I'm working to leading order, I can simply pretend that P1 is equal to its mass multiplied by these unit vectors that Mao was also using. So it's very convenient that I don't need to introduce too much the notation again. So U squared is -1, and so is U2 squared, and sigma, this velocity or relative gamma factor variable, is just the scalar product of P1 and U2. So in this fashion, the leading order soft region contribution is simply M1 and 2. The dependence on the mass is completely scaled away, and then U1, U2, L squared, and L minus Q squared, which cannot be expanded because now L is of the same, formally of the same order as Q. Now, this integral is actually elementary. You can do it, for instance, by Schwinger parameters. Let me just write down an intermediate expression, which will be useful to us in the following. By T12, I just mean T1 plus T2. And all integrals are from 0 to infinity, as usual. So, and then we have an integral of this type, x3 squared plus 2 minus sigma minus a0, x3 is 4 plus x4 squared. Now here I'm labeling the lines as follows. So the first two, T1 and T2, are associated to the massless lines, these guys here, and T3 and X3 and X4 are associated to the massive lines here. So in particular, the quantity in the square bracket is associated to the massive line contributions. Now, again, as I was mentioning, this is completely trivial in this case. You can do it explicitly, and the result is the following. Here we have the promised non-analytic contribution in Q squared that appears. I hope I get the factors right, but I will not assure anything. And here we can again do the integral also. In fact, they are factorized, the integral over the massive and the massless parameters, which takes this form. In particular, for us, let me note that as we send sigma to 1, or this additional variable sigma squared minus 1 to 0, so in the static limit, this square bracket scales as I pi to the 2 divided by 2 tau. So this is just to have a simple, full detailed case of what it means to do hard and soft regions and throw away the hard one. So before going to these more detailed aspects of boundary conditions, let me again, this is a bit selective, especially due to time reasons, and also to fit the scope of the presentation that I had in mind, which is to present some results about the massive eikonal. But let me just trace out some chain of results that have been obtained recently in this with this mindset. So first, very important result is, of course, the calculation at 3 p.m. Of the potential, namely conservative, as already explained in detail by Mao himself, calculation of the 3 p.m. Deflection angle, which in our language can be translated into the knowledge of a potential part of the real part of the 3 p.m. eikonal delta 2 in general relativity. Then sometimes later, so this calculation, of course, was done by Zwiebern and collaborators. Sometime later, Julio Paramartinez, Michael Ruf, and Mao Zeng came up with a similar calculation for n equal 8. And moreover, in the same paper, they provided us with this very nice tool of evaluating soft integrals by means of ordinary differential equations, although they eventually performed the calculation for the eikonal and for the deflection angle, restricting to the potential region. Last year, together with Paolo, Rodolfo, and Gabriele, we essentially extended this calculation to encompass the full, so including the full soft region contribution to the eikonal and to the deflection angle, again in n equal 8. This in particular solved some puzzle related to the high energy properties of these quantities. And sometime later in January, we extended this a little bit further by considering the imaginary part of delta 2 as well, and limiting in particular ourselves to the 1 over epsilon piece, this divergent part I was talking about earlier, that we calculated in both in n equal 8 and in GR using a technique based on the 3-particle cut in the S channel and on the Weinberg soft limit, although a similar calculation can be also performed by exponentiation of infrared divergences. And again in January, the calculation of the 4 p.m. Radial action, or let's say in this presentation, let me treat it as almost equivalent to the real part of the eikonal in the potential region in GR was performed. And then recently the full calculation, we essentially presented the details of the full calculation of delta 2 in n equal 8, and also extended the calculation of imaginary part of delta 2 to the whole soft region and in GR. And then combining this with all these previous results here, finally led to the full delta 2 in GR as well. And a bit later, in these two very interesting papers, one of which is on the archive today, both these calculations were independently confirmed and performed with a very nice method by Bjerumborg, Damgaard, Planté, and Van Hove. And in fact, I look forward to hear more about this in Ludovic Planté's talk. So this was just, again, to give us some motivation to go through a little bit more exercises to learn a bit more about the techniques that were instrumental to get these results. So the main idea, as advertised by Mao, as I also mentioned earlier, is that a successful strategy seems to be to set up ordinary systems of ordinary differential equations for soft integrals. So schematically, let me write it down once again, just to fix ideas. Write down equations or systems of equations of this type, where in principle, where this I basically denotes some set of master integrals that you have, in particular soft master integrals, and eventually one is just left, in particular to loop these equations can be solved very easily, going to much more clever variables than this sigma I was using here, and then can be put in the Hahn canonical form. So the solution in principle is rather straightforward, but then one faces the issue of calculating the boundary conditions. So one wants to find out the asymptotics of these master integrals as sigma tends to 1. Or again, as this auxiliary variable tau, basically the velocity tends to 0. And to illustrate this point, let me go back to the box a little bit before moving to a slightly less trivial example. So in particular, since the whole trivial sigma dependency is contained in this blue square bracket, let me copy this thing here and put it here to be discussed. So a key observation, if we want, of course, in this case, we know the answer. So there's really no point in trying to estimate the small velocity limit of this, since we can in principle take the full answer and take the small sigma limit, the small tau limit, sorry. But let's suppose that we did not know the answer and we wanted to estimate the small tau behavior. So one key observation, I think, to this effect is to note that this quadratic form in the exponent as sigma tends to 1 becomes just x3 minus x4 squared. So in other words, it becomes a quadratic form that has a zero mode. And if we draw the x3, x4 plane, we are integrating, of course, in the first quadrant of this plane. This means that there is this zero mode 1, 1 that is pointing precisely in the integration range. And this is essentially the source of this 1 over tau. You remember that we had indeed for small tau. And therefore, an idea that seems to be promising is to change variables to essentially diagonalize this and define some alpha as x4 plus x3, this zero mode coordinate along precisely this 1, 1 direction, and then some other orthogonal sorry, of course I should put x4 here. Beta, and then essentially this means slicing the first quadrant in this fashion. We can rewrite the integral as 1/2 due to the Jacobian, integral from minus infinity to plus infinity, or in the beta, integral from absolute value of beta to infinity in the alpha, and then e to the minus. And of course, to leading order, there will be this beta square that we were finding also earlier here. And then there is a contribution that indeed involves this zero mode and is regulated precisely by tau, which is going to 0. Remember, this is sigma squared minus 1. So in a sense, what we are doing is that we are imposing a further scaling condition on these two Schwinger parameters, alpha and beta, and basically the scaling condition is that beta does not scale tau to the 0, and alpha instead is scaling as 1 over tau, right, in order to get in order to have a homogeneous combination here. And then this, luckily for us, this can be factorized by taking, basically this can be neglected since it is lower order, of course, compared to 1 over tau, and it will only give rise to higher orders in tau. So these two integrals are Gaussian and factorized. The first one is just square root of pi. The second one is 1/2 because it's half of a Gaussian integral, and then there is a square root of 4 pi over minus tau squared minus I0, which is precisely the asymptotics we wrote before. So so this seems to be, it seems that it can be useful in order to evaluate these boundary conditions to look at these quadratic forms and these zero modes in Schwinger parameters. So to to further motivate the usefulness of this kind of considerations, let me consider a slightly less trivial example at two loops. This double triangle prime called sometimes, or maybe an N diagram if you draw it in the other way. So here we can take the routing in this fashion: L1 minus P1, L2 plus P3, I think. And then, okay, here let me directly focus on the soft region and not discuss the the issue about the splitting in hard and soft region for brevity. So remember that essentially to the order we are working, we can approximate in this fashion P1 and P2, and of course P3 as well, and 2U2. So we end up in the case with two integrals, L1 and L2, and then again the mass dependence factorizes neatly, in this parameterization. L1 plus L2 minus Q, which are homogeneous. Now, again, one can introduce Schwinger parameters and ends up with this kind of expression. Let me write it down and then comment it. So T is essentially a discriminant that emerges at some point, and this permutation invariant quantity. And then e to the minus T1, T2, T3 over big T Q squared. And then we have this square bracket, which is somewhat reminiscent of the structure we had for the box. But of course, here it's a bit more complicated because there is a sort of there are both massive and massless Schwinger parameters. X4, X5 plus T13 X4 squared. So here again, I'm writing down 1, 2, and 3 for the massless lines, and then I think 4 and 5 for the other ones, although they could be swapped. So again, we want to, so in this case, we don't really, I don't think the final answer of this is known for fixed epsilon, for fixed velocities, although I could stand corrected, at least I don't know it. So we just set out with the more modest goal of evaluating the limit tau goes to 0, the near static limit, and in this limit we can first do a naive thing, which is to really send tau to 0 or sigma to 1 in this expression. Let me again focus on the square bracket, which is essentially where a place where a non-trivial thing happens. And here we can simply try to set sigma to 1 and see what happens. So if we do this, we end up with a quantity whose quadratic form here is perfectly well defined, except when T1 is equal to T2 is equal to T3 is equal to 0, because it's discriminant of the polynomial in X4 and X5 is basically equal to T, this quantity here, which is basically never 0. And this does not give any problem. And in fact, this expression is finite and real. And so it seems that somehow this is fine. However, remember that the original diagram had a non-trivial three-particle cut, and so we expect this to have a non-trivial imaginary part, at least for some to some order in tau. There should be an imaginary part somewhere, but we seem to be missing it completely. So let me call this naive tau goes to 0 limit the ordinary contribution in this limit. There is another one which we can consider, and which essentially enhances the contribution of the intermediate line, the one that enters the three-particle cut, and this, let me call it singular, in the sense that we are going to give this T3 a scaling of the type minus T squared, whereas T1 and T2 are going to scale like tau to the 0. So in this fashion, we end up with an expression that looks more promising to give us the needed imaginary part. And indeed, as you can see, if we send sigma to 1 here and say that T3 dominates everywhere else, this gives us precisely an expression that we recognize from earlier on, which again has this 0 mode we were talking about. So of course, this is just the leading order in this limit. I will take into account the next ones in a second. But again, let me emphasize that this expression as sigma tends to 1 does seem to have the needed singularity and give rise to the needed branch cut as tau tends to 0. So how do we treat this thing? We can proceed again as follows. So we can, for starters, let me copy again this expression. And let me introduce the same variables that we had earlier, so alpha and beta. And then to leading order, precisely as before, we had 1/2 integral in the beta, integral in the alpha, e to the minus T3 beta squared this time. And then we have first order correction, which now also has this zero mode component. And it appears with this precise combination here. Now, we see that the right scaling that we have to assign to this alpha and beta in order to have a non-trivial scaling is order tau here, in order to compensate for the order tau squared, tau to the -2, sorry, that T3 had. And then here alpha can simply scale is tau to the 0. And let me emphasize that this is indeed a homogeneous combination, because T3 cancels the scaling that tau brings along, while T1, 2 do not scale. So again, to leading order here, we can approximate this with 0 and say that this just becomes factorized into 2 Gaussian integrals, 1/2 square root pi, and then here we have, sorry, here we also have a T3, and then here T1, 2 plus T3 minus tau squared minus A0. So this eventually has led us to the needed imaginary part in the boundary condition that we were missing with the other more naive scaling limit, and it is given by this expression. Then eventually we can plug this into the previous expression for the complete integral, and then I also need to remember the masses, and also here, of course, we need to enforce the scaling limit defining the singular region. Here T3 T1 2 becomes is the dominant part of this big T, and here T3 also cancels out, so we have a factorization of the two of two types of integrations, essentially, one over T1 2 and the other one on T3. And then luckily for us, this integral can be done exactly. Let me not bore you too much, since I've done it already for quite some time now. Let me just write down the needed, the problem is non-analytic in Q² part, and now in addition with some gamma factors that are completely straightforward to retrieve, some non-analytic in tau contribution as well, tau to the 1 minus 2 epsilon, which is also the non-analytic in tau part and imaginary part. So this, although a bit lengthy, I hope this was to some extent insightful, in the sense that this method of looking at these zero modes in the integration region can be in fact extended to more interesting integrals, in particular at 2 loops, another integral that is of course very similar in its discussion but leads to a much less to a more interesting contribution, is the one where this propagator is raised to a non-trivial power, because then the scaling becomes this one, and this is in fact crucial in order to retrieve the right boundary conditions for the soft differential equations, and in fact it also extends rather easily to setups where the number of massive lines is higher, in particular the double box and its non-planar companion. Moreover, in that case, it's also useful not only for the singular scaling where which is needed in order to evaluate the imaginary part, but also for these more ordinary ones, although eventually it's equivalent to performing the discussion of the potential region that Mao was also discussing in detail. So with that, I think I can essentially conclude what I had prepared. So let me just wrap up a little bit and mention a few words of motivation for future work. So I hope I try to illustrate a technique based on the eikonal exponentiation that allows you in principle to go from the amplitude to observables, in particular to our beloved deflection angle at 3 p.m. And I have tried to summarize a little bit recent advances in the literature in these types of calculation that have been pushed both in the maximally supersymmetric theory and in general relativity. including nice progress also in techniques of integration that have not been covering here, but they look very promising. And and I hope I presented to you in some detail, although maybe a bit boring for non let's say experts or people not really doing this type of calculations, but still, these methods sometimes can be recycled, and so I thought it could be to some extent useful to present them in some detail at least once. Some techniques that have been useful to systematically evaluate soft boundary conditions for these two loop integrals that we have been dealing with. And of course, for the future, a straightforward and obvious question is, can we go to 3 loops for this soft business? And on this, unfortunately, I don't have anything to report at the moment. And although I have to say, I can say that there are supposed to be non-trivial issues with eikonal exponentiation, in that already in the massless n=8 theory, so m = 0 amplitudes in n=8, a couple of papers due in particular to Paolo Di Vecchio, Rodolfo Russo, Steve Nakulic, I think Chris White, Andres Luna, have evidenced a clash between the infrared exponentiation and the eikonal exponentiation. This is, of course, something to be understood better. And or, as I've been hearing throughout the workshop, there have been some challenges to the choice of I-epsilon prescriptions that is not supposed to give you the right answer unless you're very careful. So, of course, this is something really interesting to be looked at more carefully. And I suspect, we also suspect, that probably both these issues have to do with a more complete and systematic understanding on how to really include radiation in a more systematic fashion in the eikonal framework. So not only including these radiation reaction effects that appear in the cuts, as we were seeing here, emerging from this singular static region, but also really including real, sorry for the pun, real particles in the exponentiation itself. So thank you very much for your attention.
Okay, great. Well, yeah, certainly I, for one, enjoyed all those details. It was fantastic to see all that stuff worked out. Thanks, Carlo. Yeah. Are there any questions?
Maybe I can ask. I have 2 questions, actually.
Please,
Sure.
So you explained how to use these Schwinger parameters to evaluate the boundary conditions, but effectively you had to assign some velocity scaling to each one of the Schwinger parameters. Isn't this basically like doing the expansion by regions and picking up the contribution from each region in the low velocity limit?
Yes, it's if you want, it's really yet another expansion by region, as you say. I think also the one we usually call expansion by region in Feynman, Feynman function space, if you want, has an analog. I mean, also the soft region and hard region as an analog in Schwinger parameter space, and in fact, it's one secretly employed by Paolo, Rodolfo, and Arnau Comanscollado in their paper at 1 p.m. They did not call it expansion by regions, but what they really did was, to go to Schwinger parameters and take scaling limits in Schwinger parameters. But this is completely equivalent to the soft hard business we have been talking about. So yes, it's really the same. Although, I mean, in the technical steps, intermediate steps have been, I think also Smirnov comments on that at the end of his book, and he says, the 2 methods are essentially equivalent conceptually and they should give the same answer, but in the intermediate steps, they are completely independent. So, these manipulations with zero modes that we've been doing are very different than reasonings about, for instance, permutations of poles and so on. So, I mean, it can be useful to compare, but I find it kind of hard to see, from the very start that you should.
Doesn't this mean that you will find the same issues with ambiguities and evaluating individual integrals that one finds if one splits it, as Mao explained? Because the problem is that you're assigning some time for the graviton propagators, and when you expand in small velocity, basically you're making it instantaneous. And
yeah, I find it kind of hard to understand, for instance, for the triangle, right? Because the triangle actually does not depend at all on the velocity. So there, I mean, it's kind of hard. I mean, when you go to Schwinger parameters, one neat thing is that you immediately see what are the invariants that your integrals depend on, and there the velocity simply is not there. So you cannot take the small velocity limit in that setup, right? So in that case, the ambiguity is not there, but simply because you're forced to evaluate it, quote unquote, exactly, right?
right.
For the other ones, we didn't find ambiguities, although, of course, assigning these scalings is a bit of an art. So you have to try all possible scalings that give rise to non-scaleless combinations, and so
Yeah,
in that
that's
sense,
what Mao was.
there is not an art, but you need some creativity to say, so to say.
Yeah, it's the usual story of you need to make sure you have all regions to get the full answer.
Exactly. So yeah,
Okay,
that issue is the same.
So my other question is about the split. When you exponentiate, you have this capital delta also.
Yes.
Right. So okay, up to 2 loops, I think there's no issue and it's pretty unambiguous. But do you understand in general like how to unambiguously organize the pieces into little delta and capital delta? Or
yeah, I mean, already at 2 loops there is this sort of subtlety, or in fact that you need to subtract, right, this interference term. So okay, already there it's not completely obvious. I mean, it always looked to me like a non-trivial test of this exponentiation, because it's the first place in which you need to go back and remember that you had some small delta times big delta, and it works apparently. In general, I try to stress that this delta is really determined by all the guys that scale in this fashion, and I think the splitting is unambiguous, right? I mean, at least the prescription. Then if it's correct or not, if it works or not at 3 loops, I cannot say because I did not try. Probably there are issues with with this IR exponentiation I was mentioning, but if you go to 3 loops, in principle, everything that scales in this way, you sweep it inside the big delta. And also, as you also mentioned, sorry, just another thing that comes to mind, since in that case you would also have, you have to dig a little bit deeper, both here and get the first term here due to these, again, cross terms.
Yeah, that's what I'm worried about, because you can have things which are like quantum squared times many iterations of the classical, like 3 level, and then what that in terms of h bar power counting might have classical scaling. The question is, where do I put it? Do I put it in delta, or do I in capital delta, or do I put it in little delta? And also,
I guess the prescription is that you put it in is that you put it in big delta if it has this scaling here, and then you can solve these relations, right? Or maybe it's also possible that I'm missing something. But for instance, from one loop you can determine big delta, and from 3 level you determine small delta, and then the would be classical part of the 2 loop level amplitude, which is the one that scales as 1 over h bar. You need to subtract the product of these two in order to get the true classical part, which is the small delta 2. So
you're saying
I was expecting this to go on, but maybe there are subtleties that I hadn't thought about.
I mean, basically you're saying this is a definition of...
Exactly, this is an answer. Then, I mean, if it's really what I mean, the correct one, I mean, again, the non-trivial test to me looks that, I mean, this one in the square brackets looks like a non-trivial test to me, because we need to subtract, for instance, in the imaginary part, this means that you are subtracting the 2 particle cuts, and this seems to work consistently up to now. Then 3 loops is a bit uncharted territory, I would say. Yeah,
but the phase shift in principle could have like h bar corrections and still be in the exponential, right? Like
this is a question I get sometimes. So it seems a bit forced to me. So I understand the logic of putting these quantities that have 1 over h bar, and then this is the classical action scaling, and then only PM corrections to that. Only small parameters, but no h bars. You see, just classical, really general relativity PM meaning corrections. but I don't have anything more profound to say than this.
Thanks.
Yeah, okay. Okay, so Thibaut, maybe you.
Yeah.
Good time for you to ask your question.
Yes, I want to ask a question. So the eikonal shows a nice exponentiation that you can check in impact parameter space. There should also be an exponentiation of infrared divergences in the ordinary amplitude without the transform. So how do they fit together, these two exponentiations?
Yeah, that's a very good question. In fact, it was answered in a couple of papers for massless n=8. Now, I unfortunately did not put here, I think, the archive number, but there are papers by Rodolfo, Russo, Paolo Di Vecchia, Tibna Kulic, and Gabriele, I think, is also there, and sometimes, at least one of the two also, Andres Luna, I think. And for these specific cases, I tried to look at it in a paper that I think appeared on the archive today, this one. And basically what you can see there is that you can indeed retrieve this imaginary part of delta 2, the divergent part, by enforcing precisely the exponentiation of infrared divergences in momentum space. So at least to these, for the data that we have available for massive objects seems to work fine. So in GR, I just use the Weinberg, result from 65, and it seems to do the job also in this case. And for n=8, again, these results by Paolo and others. But exactly as you say, you can constrain the amplitude with these two types of exponentiations. Yes. One from the momentum side, momentum representation side, and then in particular combining this with this knowledge that we have that we can just selectively focus on non-analytic pieces. This is very convenient because you can basically play Sudoku, right, and constrain just the terms that you want, and you indeed find the right 1/epsilon, it seems, at this order.
Okay, thank you.
But maybe you should mention that we did find a problem.
Yes, this is exactly. This is what I was referring earlier on. Also,
yeah, you referred. So I don't know. Maybe this is related
yes.
to Thibaut's question.
Sure. Sorry, I should mention it once again.
Yeah.
Yeah. So this is what I was also having in mind here when I say issues with exponentiation. So exactly. So there seems to be a tension between the exponentiation, the two exponentiations at starting at 3 loops in the massless theory, and and we will have to look into that. We have some hypotheses right now, but I think we should wait before we talk about that more in detail.
Okay.
Maybe if I can, I use my chairman card and interject a question before Cheshen. Yeah, so about this exponentiation and eikonal stuff. So I mean, there's this issue of the capital delta, and then also the issue that potentially things, some of these delta 3s, etc., might, be imaginary when you want them to be real. What can you say in the probe limit? So suppose you consider, scattering of, it could be 2 to 2 particle scattering, but in the probe limit. What's known there? I mean, do we know that all these things exponentiate? And presumably there should be no issue about something being imaginary when something should be real because there's no radiation.
Yeah, so unfortunately, I'm not very knowledgeable in this respect, but I can invoke the help of the public. And so I think that Rodolfo looked at this in quite some detail. Also, remember, they had numerous checks, at least at 1 p.m. in the paper with Paolo and Arnau. So I don't know, maybe Rodolfo can comment on that.
Yeah. So actually, we started from the probe limit, right? Because that's kind of easier. As you say, there is no radiation, and the same exponentiation just works. One thing I think is maybe interesting, something interesting we found just studying n=8 in the probe limit, is that the big delta that Carlo was mentioning already at 2 p.m. becomes an operator. So if you study the full n=8 spectrum, I mean, you can throw some graviton in, and then classically, it seems that you get a Ramon field coming out. For instance, if you scatter a massless state on a D-brane heavy object, right? So initially we were confused and we were saying, oh, maybe the classical eikonal becomes an operator, right? You can have this flavor changing transition, but that's counterintuitive. You don't expect that classically. And it actually, those terms are subtracted away, exactly as Carlo was saying, right? This subtraction, once you take away the big delta. So big delta becomes an operator. And then when you define small delta in this prob limit, it stays just a phase. So I think the studying the prob limit is very useful, right? It builds intuition, and then you can use it. You can recycle this intuition in the more dynamical problem that Carlo discussed.
Okay, great. Yeah, thanks for that. Chishan.
Yeah. So I have a probably more conceptual question. So as we know, this eikonal and soft result nicely capture the radiation reaction effect. But on the other hand, I also sometimes feel confused about how to interpret the result, because when we compute like T2 to amplitude, the final state have the same energy and the same angular momentum as the initial state. But from the classical point of view, the radiation reaction comes from losing energy and angular momentum. So do you have an understanding why this the soft and eikonal somehow capture this radiation reaction? And for example, if I go to 3D, like would that still be true that the eikonal gives you the radiation reaction?
Yeah, thanks for the question. So in fact, all these issues that we've been criticizing the eikonal about in the last few minutes are all related to each other, I think. And so indeed, as you say, why in the whole world are we considering an elastic amplitude and then come out with predictions about radiation reactions effects? So this is of course something, in fact, I mean, when we first found these corrections, we did not know what they were, because this is completely not obvious, right? So last summer we were not, then eventually it became clear that they were what they were. So the answer that I can give is only partial, unfortunately, even if this is a very basic and very important question. So the idea is that somehow the amplitude knows about the radiation due to its cuts. And in these cuts, if you ignore the radiation part, you know, in the belly of the amplitude, then you end up with a potential answer. But if you do not do so, you end up with this imaginary part of the eikonal, which is also not supposed to be there, right? Because if the eikonal is supposed to be correct, then eventually the S matrix should be unitary. So e to the 2i delta should be really an Hermitian thing, which it is not if delta 2 has an imaginary part. And so the right way to cure this imaginary part in small delta is that you have to treat delta as an operator and include some A and A dagger associated to the true emitted radiation. But this, of course, would involve, you know, the eikonal being a matrix in the space of processes where you not only have processes of this kind, but also processes of this kind. And you know, and the eikonal rotates, you know, between all these possible states. And what has been checked, for instance, by Gabriele and collaborators in some recent papers, not recent in the sense of last year, but a few years ago, is that at least for the soft part of this radiation, this is precisely what happens. So if you include this soft, if you include A and A daggers with coefficients dictated by the soft emissions, you indeed cure this infrared divergent part, this infrared divergent imaginary part, and go in the direction of answering in a complete way the question of, you know, how should we really interpret these corrections in a systematic approach, not really calculating our way around and then interpreting what we find step by step.
Maybe I can comment on that also, because in this other approach by Donald and friends that we used, it's even more clear that that's exactly what's happening, because apart from the two particle cut contributions, which is what you're subtracting in the eikonal, there's a part of the imaginary part of the amplitude, which is directly the 3 particle cut, that basically the square of what you drew there. And that purely cancels the imaginary part of the phase. So we find that this impulse kernel, which is basically the derivative of the eikonal phase, it's purely real after including all the cuts. So I think this should work. The question is, can one make it very explicit?
It's very clear from KMOC that this three-party cut is included, then that will include all this radiation reaction. The part coming from eikonal is not that obvious to me.
Yeah, so at next order, at 3 loops, it will be more tricky because of these I epsilon prescription subtleties, which of course in KMOC they're guaranteed to work out. But then in the eikonal, you're still using like Feynman I epsilon, and you need to give the right prescription, how to evaluate, which is a I epsilon prescription for the cuts, which might not be completely unambiguous.
Maybe also one comment is that since Dano asked about the probe limit in equal to A, and like with microwaves, we actually have the result for equal to A as well in the potential region. And especially in the probe limit, because I think there's no radiation. So I think the result for potential region, I think that should be the correct result in the probe limit. But in fact, in equal to A, it's actually 0 because there's no probe limit correction.
You mean self force?
In the probe limit.
Do you mean the probe limit is exact?
Yeah, it's the exact probe limit. Yeah, there's no higher order in G correction.
Let me see. So Thibaut, I'm not completely clear whether your hand is up again or your new question or
no, sorry.
Up.
Sorry.
No problem. Okay. It's easy to forget. Let me see. So I guess we got a link in the chat that there's, I understand, another talk going on over at GGI from Jan de Boer. Maybe it's just started around now, so it could be something people are interested in. Otherwise, Gabriele, should we?
I think unfortunately we have to stop now because of the other talk going on. But I think the discussion can be continued. I'm sure next week, for instance, there will be more on this.
Yeah, this is very interesting. It'd be interesting to hear more about it. Okay, well, thanks everybody. And I guess that's it for today.
Thank you. Thank you.
Bye.
Bye-bye.